vodcast for Equilibrium Chapter 15. You'll be using the last 3 pages of the notes outline, pages 6, 7, and 8. So when you're ready, let's get started. All right, last couple sections involve applying the equilibrium constants. So one thing it can tell us is whether a reaction is at equilibrium or not. In order to do that, to answer that question, we'll solve for something called the reaction quotient, labeled Q. Q is calculated just like K is calculated, but use values that are at the current conditions, not necessarily at equilibrium, but you can find out whether they're at equilibrium or not by calculating Q and comparing to K. So if you use current values and you found that Q equals K, as nature wants, then it means the reaction is at equilibrium. But if you have a Q value that is less, meaning there's probably fewer products, it still needs to go further forward before it has reached equilibrium. If Q is larger, you have too many products, and it needs to go in the reverse direction to make more reactants before it's at equilibrium. Let's try an example. All right, if you have a reaction between hydrogen iodide forming 2 hydrogen iodide gas molecules, and the K value is 50.5. Predict in which direction the reaction needs to proceed to reach equilibrium if we start with 2.0 times 10 negative second moles of HI, 1 times 10 negative second moles of H2, and 3 times 10 to the negative second moles of iodine in a 2-liter container. So first thing you want to do is calculate Q. And don't forget to use the molarities. Since you don't have pressure information, you'll want to make sure you take into account the 2 liters. So pause at this point, try to solve the problem, and then come back to check the answer. Okay, so the initial concentrations are going to be 1 times 10 negative second for hydrogen iodide, 5 times 10 negative third for hydrogen gas, and 1.5 times 10 to the negative second for iodide. So solving for Q, you set up Q calculation just like you would the KEQ, put in the numbers, and you get a number of 1.3. That is much less than 50.5. So that means that the concentration of hydrogen iodide must increase. The reaction must proceed further to the right before it can reach equilibrium. So the forward is still being favored. And as written, it'll proceed left to right to get to equilibrium. Okay, not too bad. Here's something else that we can do using equilibrium. We can find equilibrium concentrations. So let's say we have that same reaction and we know how much we've started with, 1 molar hydrogen, 2 molar iodine, and 0 hydrogen iodide. And we know that equilibrium constant, 50.5, oops, sorry about that. Then we can use our ICE table to find the equilibrium concentrations by knowing that the change is stoichiometric. So if we're going to lose X amount of hydrogen and iodide and gain 2 times that X amount of hydrogen iodide because it's a 1 to 1 to 2 ratio, then we know we'll have 1 molar minus X, 2 molar minus X, and 2X for our equilibrium concentrations. When you put that in the equilibrium expression, you solve for X. Now, this is one of the more complicated examples because this is going to require a quadratic to solve. But you folks can do that. You've got your calculators. You can plug it into a quadratic, and you should find, go ahead and stop and solve if you need a moment. You should find that X will be either 2.323 or 0.935. And if you think about it for a moment, you'll figure out which one is the right answer. Okay, 2.323 can't be the right answer because you have to take 1 minus x or 2 minus x, and you can't have negative concentrations. So our x value is 0.935. So the hydrogen must be 0.065 molar, iodide must be 1.065 molar, and hydrogen iodide is 1.87. All right, moving on to LeChâtelier's principle. We've been talking a lot about this so far, so let's read it out and see if we can apply it a little bit. If a system at equilibrium is disturbed by a change in temperature, pressure, or concentration of one of the components, the system will shift its equilibrium so as to counteract the effect of the disturbance. All right, so here's a visual look at this. So if you're adding or removing a reactant or product, so changing concentration. So let's say you have this equilibrium and you add something to it. Well, if you add something, you're going to make that reaction using that chemical, you're going to make that one favored. Now it'll reestablish the equilibrium by using up what you added and making more of its product. So if you add a reactant, you'll make more products. If you add a product, you'll make more reactants. Pressure. If you change the pressure by changing the volume, now this only impacts gaseous systems. So if you increase the pressure, you can think of that as increasing the concentration. And you're going to shift the reaction to reduce that pressure. And it will shift in a way that will favor whichever side of the reaction has fewer gas molecules. So lower number of total gases is favored with higher pressure, and higher total gas molecules is favored with low pressure. Temperature is going to impact a system depending on whether it's exo or endothermic differently. So if you have an endothermic reaction, if you increase the temperature, you're going to shift it right because it needs that heat to produce the products. If it's exothermic, adding temperature is going to shift it the other way because it doesn't want that heat. It wants to break it down and go in the reverse direction. So heat feeds an endothermic reaction and inhibits an exothermic reaction. All right, let's do some application to a real-life situation. The Haber process. So if you have a system in equilibrium, and looking at the Haber process, nitrogen plus hydrogen yields ammonia. It was so important during the Second World War that Haber became a millionaire when he figured this out, or a very rich man, whatever it was at that time. So if you add hydrogen, that is going to favor the forward reaction, and it's going to reestablish its equilibrium with a higher amount of product. If the ammonia is going to go up, there will be more hydrogen, and the nitrogen will get used up because the hydrogen and the nitrogen will be reacting. So adding a component results in some of it being used up. Removing a component will result in some of it being produced. So if you took out some ammonia, then that would mean the nitrogen and hydrogen would get used up to a greater extent to make more ammonia, to reestablish an equilibrium. Okay, when gases are involved, as we just talked about, that pressure or volume will affect the equilibrium. So if you have a higher volume or a lower pressure, you'd favor the side of the equation with more moles. So let's think about the Haber reaction again. Should have left it up there. So you've got nitrogen plus hydrogen. I believe you need 3 hydrogens to make 2 ammonias. And these are all gases. So you have 4 moles of gas in the reactant part and 2 moles of gas in the product part. So higher pressure is going to favor the products. It's going to squeeze them all together and want them to be more condensed, more molecules. So for Haber, one thing he figured out was to increase the pressure in the system, and that would favor the product. All right, heat also impacts most reactions, as we talked about. And so in the Haber process, it is, well, actually we said heat acts like reactant, adding to endothermic reactions, and exothermic heat acts like a product, driving it to the back toward the reactants. So the Haber process, I believe, is exothermic. And so as the gases are reacted, then they're allowed to cool, which helps them favor the product side of the reaction and makes more liquid ammonia. Now, as it turns out, cooling does help, but the activation energy is really high, so catalyst is also employed for the Haber process because you need to lower that activation energy for all of those other effects to have the maximum impact. So a catalyst increases both the rate of forward and the reverse reactions. But you can reach equilibrium faster because you're getting over those activation energies more easily. So catalysts, again, the activation energy is lowered, easier to make the transition state, and allows equilibrium to establish more quickly and at lower temperatures. All right, there we have it. Thank you very much for joining me on this journey through equilibrium. I'll see you on Wednesday. Bye.